Hi guys, welcome to the today's session of design and analysis of algorithms. In this session, we are going to discuss about one of the applications of dynamic programming, which is nothing but computing a binomial coefficient, right? So I hope that you all know about binomial coefficients. You already studied about the binomial coefficients. Now we are going to see how to find the binomial coefficient using dynamic programming. Right. Now, first of all, we'll see the general procedure, how to find the binomial coefficient. So first of all, what is a binomial coefficient? So here, computing a binomial coefficient is a very fundamental problem of mathematics and in also computer science. Now, what is a binomial coefficient? A binomial coefficient, C n comma k, can be defined as the coefficient of x power k in the expansion of 1 plus x whole power n. Now, in this, if I want to expand this term, in the expansion of this term, the binomial coefficient Cnk, C of n comma k is nothing but the coefficient of x power k. So, x power kth term coefficient. Suppose, for example, if I am taking x power 1, so what is the coefficient here? Cn comma 1 into x power n plus. What is x square coefficient? Cn comma 2 x square. Like that, we have different coefficients. So I can get up to x power n, right? So now, for every x value, we have the coefficient. So that coefficient is nothing but Cn comma k, right? Now, a binomial coefficient Cn comma k also gives the number of ways, disregarding the order, that k objects can be chosen among n objects more formally. In how many number of ways k objects can be selected from the given n objects? It is nothing but k combinations from n element set. So for finding this also, we can use this binomial coefficient, right? So mathematically, how the binomial coefficient can be expressed? It can be expressed as C of n comma 1 is equal to C of n comma k is equal to n factorial by n minus k factorial into k factorial. Here definitely the k should lie between 0 and n, right? Now, how this can be found? Here I have given one example. Let us see. That is C of 3 comma 2. So how I can write it as means n c k. That is 3c2, which can be written as 3 factorial by n minus k. N is 3, k is 2. That's why 3 factorial by 3 minus 2 factorial into 2 factorial, right? So by solving this, I get the coefficient 3c2, right? Now here the coefficient is 6 by 2, right? Which is nothing but 3. The coefficient is 3. Now, what is this coefficient? What is this represents? It is the power of, that is, if I am taking 1 plus x whole power 3 in the expansion of this, what is the coefficient of x square? The coefficient of x square is 3. The coefficient of x square is 3. Right? Like that, we are finding generally in the normal procedure the binomial coefficient. Right? Now, how to find the binomial coefficient using dynamic programming? So here, definitely we already seen in the general method of dynamic programming, the two properties should be hold if a problem can be solved in the dynamic programming. Those two properties are nothing but optimal substructure and overlapping subproblems. Right? Two properties should be hold. Right? Now, how these two problems are hold in case of binomial coefficient? Let us see. The value of C and K can be recursively calculated using following standard formula. What are those standard formulas? C and K is equal to C n minus 1 K minus 1 plus C n minus 1 comma K. By using this formula, I can find C and K, and C n0 and C n comma n, which becomes 1, which becomes always 1, right? Now, here, that is, I can write C00, C10, C20, and so on. Suppose for example, n is equal to 4 means C44. These two values becomes 1. Otherwise, the Cnk can be calculated as C of n minus 1, k minus 1 plus C of n minus 1 comma k. So what this represents means we represented this problem as subproblems in the same terms. I represented the same type of subproblem. Here, I can take n minus 1 as n, k minus 1 as k. If I am taking it as Cnk, same type of problem. So if I am taking n minus 1 as n, it becomes Cnk again, right? That is, we are dividing the problem into two subproblems of similar type, right? So that's why it is following the optimal substructure. So that is, we will find the optimal solution for this. Then we will find the optimal solution for this. These two optimal solutions are added to get the solution, optimal solution of given problem, right? Now, how overlapping subproblems can be folded here. Okay, now here you can see, for explaining about that, here I have taken an example. One is n is equal to 5, here k is equal to c, k is equal to 2. Now, what this becomes? C of 5 comma 2, C of 5 comma 2. How it can be solved is, C of 5 comma 2 is equal to, how this can be solved? C of n minus 1 comma k minus 1. That is, C of 4 comma 1. N is 5, n minus 1 is 4. K is 2, k minus 1 is 1. Next, C of n minus 1 comma k. C of 4 comma 2. This is one subproblem and this is another subproblem. Right. If I find these two subproblems, if I add these two subproblems, I will get the solution for this problem. Now, again, how this can be solved? Again, recursively, this also divided into subproblems. Now, here n is 4 and k is 1. How it can be divided? C3 comma 0, C3 comma 1. Right. Again, here I already know that C3 comma 0, whose value is 1. Here this value is find as 1. Again, for solving this one, I need to again divide it into subproblems. Here I'll get C2 comma 0, whose value is 1. And here again I'll get one more subproblem, which can be solved by again dividing it into subproblems. So here I'll get C10, C11, whose values I found as 1 comma 1. Right. Now again, this is for solving this one, I need to divide it into two subproblems. For solving this one, I need to divide it into two subproblems. For solving this also, I divided it into two subproblems. Right. Now, here the solution of this problem is known, and this can be solved using two subproblems. This can be solved using two subproblems, and this subproblem solution is known. Right. Now, by adding all these solutions, I can get when I am approaching in a bottom-up way, I can get the solution of this final subproblem C5 comma 2. So here you can observe that C31 is appeared once here and the same subproblem appeared here. That is, same subproblem appeared for 2 times. Now in the same way, C21, C21, C21. So this is appeared for 3 times. Right. In the same way, C11, 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 which is also appeared for 3 times. Right. So like that, same subproblem appears for number of times, which are to be called as overlapping subproblems. Right. So I hope that you understand how this particular problem holds optimal substructure and overlapping subproblems. So since it is holding all these things, we can say that we can solve this binomial coefficients application by using dynamic programming. Now let us see how we are going to solve. Let us see. Now here, the optimal substructure can be expressed in terms of a formula as like this. Cij is equal to 1 if I is equal to j or j is equal to 0, and that is equal to Ci minus 1 comma j minus 1 plus Ci minus 1 comma j otherwise. Right. So here if I is equal to j and j is equal to 0, if these two conditions are hold, we can represent Cij value as 1. Otherwise, Cij value becomes this one. Right. Now here you can see n is equal to 0. When I am taking n is equal to 0, C00 is equal to 1 since I is equal to 0. So here I is 0 and J is 0. Both are equal. In that case, if both are equal, Cij becomes 1. Next, coming to n is equal to 1. So here I have two coefficients. One is C10 and another is C11. C10 means, so here I is 1, J is 0. So here when J is 0, I can take it as 1, right? Its value becomes 1. And here you can see Ij both are equal. In that case also it becomes 1. Now when n is equal to 3, I have three coefficients. What are those three coefficients? C20, 21, 22, right? 20 becomes 1, 22 becomes 1. What about this 21, C21? Now how this can be solved? This can be solved as C, so I value is 2 means I minus 1 means 1. J value is 1 means J minus 1 means 0 plus C1 comma J value is 1, right? What is C10? I already calculated its value as 1. What is C11? C11 is also calculated as 1. Now finally, by adding these two, I'll get its value as 2. That is C21 value is 2. In the same way, I can calculate for n is equal to 3 and n is equal to 4. Right? So here in every loop, I throw of Pascal's triangle using I minus 1th row. So here you can see I value builds the Pascal's triangle 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. Like that, a Pascal's triangle is built. So based on that Pascal triangle only, we are solving the binomial coefficients problem in dynamic programming. Now, at any time, every element of array C will have some value, either 0 or more. In the next iteration, the value for those elements comes in the previous iteration. Now, how I can represent it as a statement means Cj is equal to Cj plus Cj minus 1. Now, so how this can be represented by using the next one. Now, here you can see I am taking n is equal to 4 and k is equal to 3, C4, 3. Now, how I can represent? So, all the elements of array C of size 4, k plus 1 are initialized to 0, right? So, first I am initializing all to 0. C of 0 is 0, C of 1 is 0, C of 2 is 0, C of 3 is 0, and C of 4 is 0. So, first initially we need to make C of 0 as 1. Here I made C of 0 as 1. Now, for I is equal to 1, I am going to solve. When I is equal to 1, C1 is equal to, according to the earlier formula, how I can represent C1 is equal to C1 plus C0, right? So, here J is that value, Cj plus Cj minus 1, right? So, C1 plus C0. Here already C1, I know that C1 value is 0, 0 plus C0 value is set to 1, 0 plus 1, which becomes 1. Here C11 is equal to 1. Right. Coming to I is equal to 2, C2 is equal to C2 plus C1. Right. C2 is 0 plus C1 is already calculated as 1, which becomes 1. That is C22 is equal to 1. C1 is equal to C1 plus C0 here. Right. Now, already I calculated C1 as 1, C0 as 1, which becomes 2. C21 is equal to 2. Right. So here I find when I is equal to 1, here we have only one coefficient, C11. But when I is equal to 2, I have two coefficients, C22 and C21, right? When I is equal to 3, I have three coefficients, C3, C2, C1. By that, from this I can get a C33, from this I can get a C32, from this I can get a 31, C31, right? Now I need to calculate all those four, right? Now the coefficient of here I want to find C43. So here C43 value, I find it as 4, right? The coefficient is 4. That is x cube coefficient. In the expansion of 1 plus x whole power 4, in the expansion of this term, I can get the coefficient of x3, x power 3 as 4, right? So by using these simple formulas, you can calculate the binomial coefficients using dynamic programming. So I hope that you all understood how to calculate the binomial coefficients in dynamic programming in a very easiest way. Practice other problems, some more problems. Thank you for listening. Thank you.